So intermediate value theorem. It says if you have a function f, f is continuous. Continuous where? On the closed interval from a to b. Closed interval from a to b. That means both a and b are included in that. Not open, has to be closed. And f of a does not equal to f of b. And k is any point between or any value instead of point sounds like more logical than point. K is any value because it's a y value between f of a and f of b then there has to be at least could be more than one value or one number between, we'll call C, and that's in the range between A and B, somewhere between A and B, where f of C equals to K. It has to be. So an example, explain that. If we have a function like this, let's see if that fits the criteria. This is A, and this is B. Is the function continuous from A to B?
Yes.
Good. Do we have a closed interval A to B? That means is A a closed circle, B is a closed circle?
Yes.
Yes, that we fit the first two. Is f of A different than f of B? Notice this is f of A. This is f of B. Are they different from each other? Yes.
Yes.
If you pick a value between A and B, any number, somewhere here, K we'll call it, any value between A and B, there has to be at least one value in that function, which is this number. There has to be a point, we'll call it C, which is between A and B, where the value of the function at C will equal to K. That's what that means. There's a point between A and B, at least one, could be more than one, where the value of the function at that point is equal to K. How can you have more than one? How about this one? Is that a continuous one? That is continuous. Let's go like this dotted line. From A to B, closed interval, very good. F of A does not equal, I made one higher than that, I don't know if you can see it. This is f of A. And right there somewhere is f of B. I made them a little bit different. There has to be at least one point. If you pick this point here, K between A and B, there has to be a value right there. Where the value of the function as C equals to K. This is one point. What I should have done actually, maybe what I should have done is loop this back up there, then you'll have two of them. You know, if I loop this back up, then you will have two of them. If I went like this, this is B now. How many values do you have now? Lots of them. See them? There's another one. There's another one. So you could have 3 of them actually, 4 of them between a and b. So you could have more than one. It says if you have a function that's continuous from a to b, that's continuous. F of a does not equal to f of b. And if you pick a value between a and b, we'll call it k, there has to be at least one point where the value of the function is equal to that. That's this, and that's this one right there. You have 3 of them here.
That's equal to what?
F of c equals to that number. The y value of that function, f, the value of the function at this point is equal to k. The value of the function at this point is equal to that number. The value of the function at this point equal to that number. So let's see what that question number 17, does that fit the criteria? So number 17, section 2.4. We have f of x. Right now it means really nothing to us. This has to be a number. You'll see that down the road if I'm trying to find the root of an equation. I can use that logic. Notice if I have a function and you're looking to see where the function crosses the x-axis, you're trying to find the roots. If you have this function, you go, well, I call this a and I call this one b. That fits the criteria. I can say there has to be at least one point where the value of the function equal to 0. If I pick 0 here, I said, what function has a value of 0? This one tells me there's at least one root. At least one root. So we use that to find sometimes the roots. As I said, right now means, oh, big deal if there's a value there. But that's where we use it. Verify that the intermediate value theorem applies to the indicated interval. Find the value of c generated by the theorem. They're saying there has to be a point where the value of the function at that is equal to 13. Let's see if that's true. What is that x value? If you graph a quadratic equation, what does it look like? That's a quadratic equation. It's a parabola. I'm not really sure exactly where the vertex of that parabola is, but when it's 0, we have a 1. When it's 6, that's 36, 37, 43. Something like this. This is 6. This is 0. The value of the function at 0 is what? What's f of 0 equal to?
1.
1. What's the value at 6? 43. Now, if you pick a number between 1 and 43, and they chose the 13, you see the 13 they wanted? If you pick the 13, it says there has to be at least one value here where between 0 and 6, that's what the mean value theorem says. It has to be a number between 0 and 6 where the value of the function is equal to 13. Well, let's prove it. Balthazar. Was you there at the restaurant in Ludlow on Friday night? Yeah. No? Just looks like you, sounds like you. No. I was about to go talk to him. I swear, I thought it was you. Okay. I said hi to the guy, he didn't say anything. That's like, hello, Mr. Balthazar. He looked at me like, what the hell are you talking about? So that's what the theorem said. Let's plug it in. Let's set this answer to 13 and see if the value is going to be between 0 and 1. Now, we're probably going to get more than one answer. Why? Because it's a parabola. What does the graph parabola looks like? There's a second part probably right there, right? So it might be 1 right here, negative value. But I don't care about that because I'm looking for this number. It has to be a value between 0 and 6. where the value of the function will equal to 13. Do we have one between 0 and 6? So how do we solve this? Move the 13 there. Is that negative 12? Can we factor that? And what do we have? X equals what? Negative 4, and the other one, x equals what? 3. Is 3 between 0 and 6?
Yes.
So we proved the mean value theorem there. Intermediate value theorem, sorry, the mean value is 1 over b minus a. We proved the intermediate value theorem. It has to be a number between 0 and 6, and the value of the function at that number is equal to 13. I bet you if you take the 3 and plug it in here, you will get the 13. Again, there's two of them, but our interval from 0 to 6. So we don't care about the other one.
What if you got the answer but you couldn't factor it out evenly? Like, what if it was a prime number?
Then that's actually, there's another method called finding the roots using Pascal, and that's coming up later in the course.
Well, because, I don't know, mine's, I don't know.
You could use the quadratic formula for this problem, because that's x squared, right? But if it was x to the 4th, for example, x to the 3rd, if you encounter a problem that says x cubed plus 7x equals 12, and you want to solve that, if you don't have a graphing calculator, which you can't use on the test, there's other ways of doing it. And that's coming up actually in chapter 3. End of chapter, the last thing in chapter 3. Using the derivative.
Well, mine's x squared plus 2x plus 2, where f of c equals 17.
Quadratic,
Set that up. It's x squared plus 2x plus 19. So how do you factor?
quadratic formula. Minus b plus or minus the square root of b squared minus 4ac divided by 2a. You don't have to factor it, right?
All right, we learned that.
Better know it. Everyone see, like, if you couldn't factor it, you have to go back to the quadratic formula. X equals minus b plus or minus square root of b squared minus 4ac divided by 2a. You can only do that if it's a quadratic equation. If it's not a quadratic equation, well, rephrase that one. If you have something like this, x to the 4th minus 6x squared plus 19, you can use that on it. Right? How? You can let t equals x squared, right? And that becomes what? T squared minus 6t plus 19 is equal to 0. So when you solve this, your answer is going to be for t, which is equal to x squared. Then you take the square root of that. So first I said you can only use that if it's quadratic. But this is not a quadratic. It's reducible to quadratic. So there are some cases where it's not a quadratic, we can still use it as long as you can reduce it. If this one was x to the 4th minus 6x cubed plus 19, start praying, because quadratic does not work here. Let me try 18, another one, using the mean, intermediate value theorem. I got my mind set up on the mean value theorem. That's coming up later, I think chapter 3. And this one,
this is number 18?
18, yes. And they want it from 5 over 2 to 4, which is good for us. F of c equals 6. That means we need to find a number between 2.5 and 4 where the value of the function will equal to 6. The reason they gave you 5.5 to 4 because this function is undefined where?
1.
At 1. X cannot be 1. So if they said from 0 to 4, you couldn't do it. Remember, your function has to be what? Continuous. So there is a hole in this function at x equals to 1. Outside that should be continuous. So it is continuous. I have no idea what the graph looks like, and I could care less for it. Let's see. Do we have what f of a? Do we know what f of 5 over 2 is? Plug it in, because I got to make sure the value of the function here and there are not equal. If you take 5 over 2 and square it, that's 6.25, I think. Is it? Plus 2.5. 5 over 2 is 2.5. 5.2 minus the 1. 2.5 minus the 1. So what do we have? 6 and 8. 8.75 over what? 1.25. Why am I putting pressure on myself? I have a calculator somewhere. $8.75 divided by 1.25. 7. And what's the value of the function at 4?
I think it's 1.5, not 1.25.
1.5. I like the 2.5 better. It gives me a whole number. See, calculators are good. 8.75 divided by 1.5. 5.83. What's f of 4? That's 16 on the top, plus the 4 over what? 4 minus 1, 20 over 3. So that's 6.67, is it? What am I doing this? Killing myself. 20 divided by 3, 6.67, yep. So, good. F of A does not equal to f of B, because that's the second condition. They can't be equal. It's continuous, yes. F of A does not equal f of B, that's good. Well, then theory said it has to be a number between 2.5 and 4 where the value of this is equal to 6. So let's take this one and set it equal to 6 and solve it. See if we can prove that. Set that equal to 6 and solve it for x. And if our number happens to be between 2.5 and 4, we've proven that theorem. How do we solve this? Multiply everything by x minus 1, both sides. X squared plus x equals 6x minus 6. Bring everything to one side. X squared minus 5x minus or plus 6. I think the software likes me. I'm getting all these good numbers. So we have two solutions. What? X equals to 2. X equals to 3. We can't use this one, but we can use that one. Why? Because the number has to be between what? 2.5 and 4. So yep, they were right. There was a number between 2.5 and 4, happens to be 3, and the value of the function at 3 is equal to 6. So that's how you prove them. You find that number and you go, oh, they wanted to put that number in. Yep, there is 1 at 3. Is it good with that one? Good. Makes sense?
Why doesn't 2 work?
Because it's not between the limits, it's between 5.5. 5 over 2, which is 2.5, and 4. So it has to be between these two numbers. And the 2 is outside that range.